So it's with a special excitement that I'm pleased to welcome Dr. Paat Rusmevichientong to our weekly meeting, weekly seminars at Google. So Paat is a professor in the Marshall School of Business at the University of Southern California, and I've been very delighted to have Paat as my PhD co-advisor. So Paat has done great work in data mining and stochastic optimization, and then for that he won several awards, including Danzig Dissertation Award, NSF Career Award, and Inform Junior Faculty Paper Competition Award. Not only he's a great researcher, he's also a great and outstanding teacher. He has been chosen as a Teacher of the Year when he was a faculty at Cornell, and then at USC he also won Golden Apple Awards for teaching undergraduate students and also teaching MBA students. And so today Paat is going to talk about the limit of rationality in choice modeling. So please join me to welcome Paat.
Thank you. Again, so this is a joint work with my colleague, Professor Srikanth Chakrabarty at NYU Stern. But now, before I begin, I really want to thank Megan here and Wahab for inviting me here. It's my first time at Google, allowing me to share with you some of my work. That's a really wonderful visit. Thank you. Thank you very much. So the focus of today's talk is on discrete choice models. Okay? And it's been really very popular both in academia and industries for demand predictions and demand forecasts. Okay? And again, the reason for that is because they can capture complex substitution patterns. And now there are thousands, if not tens of thousands of papers that have in economics, marketing, psychology, and operations that have applied discrete choice models in a variety of different contexts, transportations, retails, anything involving choices. Okay? And listed here are just a few of the tens of thousands of papers in that topic. But what I want to do is, before I begin, I just want to make sure that we all sort of set a context of what is a discrete choice model. Okay? So we have typically a universe of n product, indexed by 1 to up to n. And essentially, the one thing that we want to understand is what's the probability that a customer will choose a particular product from an assortment S. The idea here is that it has been observed empirically and experimentally that the probability that the customer will choose any one item is not exogenous. It is contingent on the assortment that you offer alongside him or her. When you go to a store, the probability of choosing a particular brand of cornflake is contingent on what other brands of cornflakes or what other brands of cereals it's present at that. And this is the quantity that we want to understand. So notice that it is not a function of the product, but it is a function of product and the assortment that accompanies it, which is offered. Okay? And that's what we want to try to estimate. So and later on, I'll talk about the data set that we typically get that we use to estimate that. But the entire talk revolves around this quantity. That's what we want to understand in discrete choice models. Okay, so one of the most popular discrete choice model that we can use to try to estimate this probability is what we call the random utility maximization class of discrete choice models, or RUM in short. Okay? And this is a very popular, again, virtually every single paper that has used discrete choice model, that model falls in this class. Tens of thousands of papers written on it. And it really assumes a very simple assumption. It says that when a customers walk in and see different choices, he or she draw a random sample of the utilities of the different products from whatever distribution you like. And then once he or she observes those sample utility, he or she picks the item with the highest utility. That's how he selects. Now, of course,
it's cardinal or ordinal?
It's not cardinal, it's ordinal. It's not order. It's not order. So it's just like a subset. And of course, no, this is not real. Nobody has utilities. Nobody has random or random. These are all modeling assumptions. Okay? But surprisingly, this simple assumption encompasses a very rich and broad class of choice model, including the multinomial logic, the nested logics, the mixture of logics, which are used virtually like in every papers in choice model in marketing. So they use mixture of logics. Okay. And so that's sort of the setup. So we want to understand the power of this RUM class. And this is the question that motivated all of this research 2 or 3 years ago is really sort of something I face all the time as I work in this area is how to select a good choice model. And typically you start with data sets. Okay? And for this particular talk, we'll be focusing on grocery sales data from a chain of supermarkets in the US. And we'll have sales transactions from multiple product categories. So what we would do, we separate them into different categories and work with each one separately. Okay? For each product category, the data set that we have can be represented by this vector F with a subscript M. Okay? What is this? This M here is a collection of different offer sets that the customers see. Now, why do we have different offer sets? Okay, so here's the one example. Different stores within our supermarket chain can carry different assortment of, let's say, soup brands to cater to the local taste. So people in New York may prefer different brands than people, let's say, in Wisconsin. But even within the same store, for example, since these soup brands have to be stocked, say on a weekly basis, during the course of the week between replenishment time, items get sold out. That happens. So when that happens, when the customers go to the store, there's an actual brand of soup that he or she sees on the shelf would be different depending on what items are stocked up. That's why we have different offer sets. And for each offer set, FS, let's use my finger then. S in the collection M. The data we observe is this FIS with the fraction of times that a product I has been purchased when the assortment S is offered. Okay? And the sum of FIS, I and S is equal to 1. Okay? So that's the data sets that we work with. And again, we can then use, given this data set, we can estimate the parameter of the choice model. Okay? It could be the multinomial logic choice model or whatever specification of the model that you're interested in. Right? The details of which is not germane in this particular talk here. Okay. And I've done that here for 6 different product categories in our data set, ranging from shampoo, mayonnaise, diapers, up to sugar substitute. For each of the product category, I fitted a multinomial logic choice model. It's a very popular choice model within the RUM class. I evaluate its performance using this metric called the mean absolute percentage error, which is the difference between the actual observed percentage, FIS, and the prediction, FIS, hat, and divided by the true value. And this is what it looks like. Now, of course, we can fit a more complex choice model, such as the 15-class mixture of logics, which has 15 times the number of parameters of the multinomial logic. And when you evaluate its error, it's looking like this green bars here. Now, this simple graph here raises a whole host of interesting questions, I think. For one thing, one can ask, like, well, what if I fit a 30-class mixture of logics or a 50-class mixture of logics? Is it possible to drive this error bar all the way down to 0? Okay, and if not 0, what is the minimum achievable loss that one can obtain for an arbitrary discrete choice model from a random utility maximization class?
These are testing errors, right?
Pardon?
These are errors on unseen data, right?
Oh, actually, you can put it on unseen data. I'm just talking about in-sample error. Just on the in-sample error. Can you drive this to 0? That's the question. So if not, what is the minimum achievable one? Okay. And of course, both of these multinomial logic and mixture of logic belong to this RUM class. So one way to state this LOR, or limit of rationality, you can write them as, well, we pick your favorite convex loss function. It can be anything. It can be the mean absolute percentage error. It can be your KL divergent, which is your maximum likelihood estimate criterion. It could be norm, 2 norm, P norm, whatever you like. Any of your convex loss functions, whatever is fit your applications. We're going to measure the distance between the observed choice fraction, which is our data set FJS, and the predicted choice fraction XJS that is consistent with an RUM model. Okay, so XJS is the probability of choosing product J from an assortment S under an RUM model. And yes?
Isn't it true that everything can be an RUM model? Because you can actually get for every person population to create the preference that he prefers what he bought
No, that's not possible because an RUM model imposes very restrictive constraint that the probability of if I add an item to assortment, the probability of choosing a single product has to go down. So that does not always happen. There could be situations in our data sets where some items, when you add it to the assortment, the probability of choosing particular items go up. Okay? So it's not always true. It is not always true.
Is it true? I guess. Can you verify that that is actually what's happening on the data?
Yeah, so that's part of that's exactly what we are trying to do. We want, because the problem is like this one is, you can verify it for a particular choice model, but we want to verify it for all RUM choice model at once. And that's part of that's what we are trying to do here. Whether or not, we want one way to frame our question is the data completely explainable by an RUM choice model? Okay. That's one of it. Okay, so this is one way to formulate this limit of rationality. Now, of course, this is not a precise mathematical statement because it's not clear how one would optimize over X, ranging over all possible RUM choice models. There's uncountably, infinitely many RUM choice models. But to do that, what we want to do is take advantage of one very important and very special property of the RUM class. Every choice model within the RUM class corresponds to a probability mass function over the set of rankings. And the reason for that, within the RUM class, I said that the customers choose product with the highest utility. What that immediately means that the magnitude of the utility doesn't matter. What matters is the ranking of the utilities across all the products, and therefore the probability mass function over the rankings. So what I can do then to make this a precise mathematical object that we want to study, I can introduce auxiliary variable lambda sub sigma. One variable for each ranking sigma. It is non-negative, and it sums to 1. So this is a bona fide probability mass functions over the set of rankings. Then we can replace this sort of fuzzy constraint xjs by a precise mathematical statement saying, well, what's the probability of choosing product J from a subset S? Well, we simply sum over all n factorial ranking sigma. And for that ranking of item, we check whether or not J is the top ranked item in S under sigma. If it is, you pick up a 1 and you pick up that weight of lambda sub sigma. Okay. This now is a precise mathematical statement of what we mean by the limit of rationality. And it's not very useful, however, because this is a convex optimization over n factorial variables. N factorial just explodes, you know, for like n equal 10, you don't know what to do with it at the moment. Okay. So, but it is a precise mathematical statement. Okay. Now, in the next probably 30 minutes or so, I just want to answer 2 questions. Okay. The first question is what I call the so what question. Let's suppose that we can compute this value exactly. Or, I mean, who cares? So what? How does that help us select a good choice model? Which was the very first question I motivated in the very beginning of the slide. That's the first question. And I'm hoping to answer that in the affirmative, that there is some use in knowing this value of limit of rationality. And then if I get that out of the way, then the next question is how can we go about and compute this value? Okay. Now, to try to figure out how to use this limit of rationality, here's one sort of, shall I say, cartoonish or pictorial representation of what we're doing. If I represent all discrete choice models within the RUM class in this big blue oval, then inside that, we have this smaller gray circle, which is a subclass of all the multinomial logic choice model. And this dot here is our observed choice fractions. This is the data set that we work with. Then I can compute the distance between the red dot and the black dot here. With the red dot here is the best fitted model in the RUM class, best fitted under your favorite convex loss function. So that distance is what we call the limit of rationality. Now, of course, we can also compute the distance between the black dot and the green dot, which is the best fitted MNL. And that is the total loss under the MNL. So in every data set that you work with, you have 2 numbers, total loss under the MNL and the limit of rationality. Okay? And you can plot them on this 2-dimensional graph. The x-axis being the total loss under the MNL, and the y-axis being the limit of rationality.
One question. The limit of rationality depends on the convex function that you chose, right?
Yeah, that's correct. Yes, that also depends on, but the methodologies of how you can go about that is up. Yeah, in general. That is correct. Depending on, a lot of people use maximum likelihood estimate, which is the KL divergence. That's also awesome, but some people prefer a different metric. So really depending on the applications.
So I can actually come up with my
absolutely
convex function that will give me a limit of rationality equal to 0.
No, you can't do that, right? Because that's not always possible because
my convex function is 0.
Well, yes, but that's not a very interesting convex function.
I know, but I'm saying you can come up with.
Yes, well, typically what we want to do is we want convex function that is sort of strictly convex and is only at 0 if your prediction is exactly equal to your observed choice fraction. Okay. Yes, but of course, if you come up with a trivial convex function, but that's correct. So, but for the 6 data sets that we have shown you earlier, you can plot those 2 pieces of information on this scatter plot. And you can see here that this plot is consistent with the pictures that we have here, that the total loss under the M&L is larger than the limit of rationality. This is so far below the 45-degree line. Now, so the question is, you say, okay, what do I do with these 6 scattered dots on this graph? Okay. Now, typically what happens is when you work in a particular application, the user often has in mind what he or she consider as what he calls acceptable loss threshold. So I think this is good enough. Now, again, of course, there's nothing magical about those. It's really user-dependent and context-dependent. But if suppose that users specify a threshold of 30%, for example, it's going to be other numbers, depending on the objective you use and the criteria you have, it immediately partitions the lower half regions into 3 different parts. The first part here, as highlighted in greens, are all those data sets or product categories for which the total loss under the M&L is already below the threshold. Okay, so if this is really your threshold, then you don't need to go further. The M&L is good enough. But we also create another segment, which is highlighted in purple here, for which the total loss under the M&L exceeds the threshold, but the limit of rationality is below the threshold. So you can sort of consider fitting more complex choice model within the RUM class, like mixture logits, nested logits, and things of such sort. And of course, there's left with the third region, which is what we call highlighted in red. These are the data set for which the limit of rationality is above the threshold. Now, it's good to know this, because what that means is don't bother fitting mixture. And fitting mixture takes a lot of work. You don't just throw it in. You have to tune them, you have to look at them. So that's so for these data set, the RUM class will not be able to allow you to have an error below the threshold. In order for you to have the error below the threshold, you have to go beyond the RUM class. And so this is one simple way that you can use this quantity, limit of rationality, in terms of trying to figure out which data set, which model to use for different data sets. And again, in our paper, we have a much more extensive discussion of how you can use this metric for model selection. So this is one way to do it. So hopefully it give you a sense that it is somewhat useful to compute this number. Yes?
Why can I just go to the most complex model all the time and then?
But what is the most complex model? That's the question. A most complex model is not 100. It's not
the one that let's say the fanciest RUM model that you have.
But that is not precise. There is no such.
But you're saying right now, like for the purple region, like you should be fitting. You can fit more complex RUM.
Oh, okay. So currently that's one. But right now the most complex, fanciest model within the RUM class is the probability mass function over ranking. Now, there are some drawbacks with those, because currently, as of now, today, fitting, we have no way to incorporate features, prices, average user reviews, and all those contextual information when fitting a probability mass function over rankings. That's an open, active research questions that people are spending time doing. So you can fitting the more complex choice model, but maybe marketers or the people who in that application, they want something interpretable. They want to understand how prices, how average user reviews, how the contextual information influence these probabilities. And for those, you need parametric models. And parametric models are not the most sort of complicated Does that? So okay, there are.
I mean, I understand that you have a universe of models that you can fit.
Yes, correct.
That have some restrictions, let's say, because you want it to be interpretable or
yes, all that.
Out of all this universe, why can't I just choose the most complicated one?
Well, you can, and that's exactly what we're about to do. But fitting that most complicated model is it's an NP hard problem.
It also might not be very predictive. You don't always want the most complex.
But my point is, why do you need what do you gain from the LOR, right?
Well, the LOR is telling you what is the loss that you get from fitting the most complex.
Yes, I know.
Rule out using it.
I mean, you're gonna end up like if I'm on the green region, I don't lose anything from using something that I would have used in the purple region, right?
Sure.
But what if you're in the red region?
Yeah, so it's super useful in the red region. Right?
Yeah, what if you're in the red region? In the red region says, don't bother. You need to go beyond the RUM class. This is the part that I'm.
Yeah.
And again, obviously, in our papers, we look at more than 6 product categories. I'm only showing you here for the slide constraints. Okay, so let me also talk about literature on stochastic rationality. Now, there's really a lot of literatures in economics and computer science that have really studied these issues of stochastic rationality. And in the economics, researchers have developed really beautiful characterizations. It's necessary and sufficient condition for when the data set can be completely explained by RUM model. So in other words, when the limit of rationality is exactly equal to 0. It's a really beautiful graph from the late 70s, Professor Falmarge, up until like as recently as early 2000 by Professor McFadden. Now, of course, unfortunately, they don't address the important questions of what happened when these necessary and sufficient conditions are not satisfied. So when the limit of rationality is not 0, and you need to go figure out what that is. And what is that number? Okay, so that has not been addressed in the economics literature. But in the CS literatures, they have looked at computing this limit of rationality for a very specific collection of subsets consisting of pairs of products. It's just all subsets of size 2. And this, even for pairs, computing the limit of rationality is provably NP hard. And there's like beautiful, like lots and lots of works, in the early 2000s, and recently to come up with approximation algorithm, how you approximate that balance. This is NP hard to compute. But they don't really look at general collection of subsets. So our goal in today's talk is we want to study this object limit of rationality for an arbitrary collection of subset M. And I think what is important to us, I think for me personally, is to really understand what about this collection of subset M that makes computing limit of rationality hard. We know it's hard when it's paired, but when we started this project 3 or 4 years ago, like burning question was like, okay, but I work in operations. I don't really encounter pairs of products very often. I encounter different kinds of subsets in grocery stores where items are stock out. Or I encounter a nested collection when airlines close or open different fare classes. Are those subsets easy to compute, the limit of rationality? So that's sort of really the driving force that we are going to go after for the next, let's say, 15, 20 minutes or so. Okay, so that's really what we're going to be going after. So again, this is listed in blue here is the formal definition of the limit of rationality I described to you a couple of slides ago. Now, I want to try to find a way to get a handle on it because it's like a very complicated object here at this point. So the first thing I want to do is try to find a way to rewrite this feasible region in a more compact way. And the first observation I want to make here is that this xjs, the probability of choosing product J from an assortment S, is really nothing more than a convex combination of these indicator functions. Because all the lambda sigma sums to 1. Okay, so you can then write this vector x as being in a convex hull spanned by n factorial vector, 1 vector e sub sigma for each ranking sigma. And this vector e sub sigma is that vector of indicators, right? So it has a binary vector of dimension equal to the total cardinality of every set in the collection. And again, if you look at the typical JS component of this vector e sub sigma, is simply 1 if product J is a top rank item in the set S under the ranking sigma, and 0 otherwise. Okay, so that's, again, haven't done anything. I'm just rewriting the feasible region so it's a convex hull. It's still equally hard. This convex hull has n factorial extreme points, 1 extreme point for each ranking. So that's a lot of extreme point to visit. So then the next thing you want to do is deal with this arbitrary convex loss function. Because right now you can use whatever convex loss functions that's fit your application at hand. It's a little difficult to deal with arbitrary convex loss functions. So what we will do then, we will appeal to this Frank-Wolf algorithm or conditional gradient methods, which allows us to solve any convex minimization problem by transforming them into a series of linear programs. Okay, so what it does is it generates a sequence of feasible solutions. In each iterate, it looks at the objective function at that point, and you linearize it. So instead of looking at the convex, you linearize it by taking the gradient at that point. Okay? And then what you do is you solve the corresponding optimization problem, which is now a linear program. And you linearize the objective function. So the CJS is the gradient of the objective function at the current iterate. Okay.
So
yes.
I have a question about this sigma. So if I give you a distribution over if I give you a distribution over ranking,
yes,
can you give me like an RUM model?
It is
that corresponds to that particular distribution.
Oh, but
is it
but once you tell me a distribution over ranking, it is already an RUM model. It is already an RUM model.
So can I come up with it like a?
Perhaps you're saying perhaps a different question is like, suppose I give you a parametric model like an MNL or a nested logic. Can you come up with a probability of distribution over ranking?
But calculating this way can be really difficult.
It's very difficult. Yes, that is correct. That is correct.
Okay, but any distribution
over ranking is automatically an RUM model by definition. Because remember, you don't need the utility values. You just need the rankings and products. Okay. So again, we essentially so there's a lot of experts in this room who work with Frank-Wolf and conditional gradients on a daily basis on a multi-billion variable. So I will leave this here as what essentially we have done is we have converted the complexity of computing the limit of rationality under this convex loss objective with the complexity of solving this linear program. Okay. Now again, this is still a hard linear program because this feasible region is a convex hull with n factorial extreme point. That's a lot of extreme point for the simplex algorithm to visit. Okay. But at least it's a linear program. And the first thing we can do with a linear program is that we can write this continuous optimization problem as an equivalent discrete optimization problem because we know that the optimal solution of a linear program occur at extreme points. And the extreme point of this feasible region is just a ranking sigma. Each ranking sigma gives us a vector E sub sigma. So we simply replace this YJS by the JS coordinate of that vector E sub sigma, which is the indicator that check whether J is a top rank item and S under the ranking sigma. And again, this is also called the rank aggregation problem, which has been extensively studied in computer science in the early 2000s and even now. And that typically occurs, the name occurs because it arises in setting when you have rankings of website from different search engines and you want to aggregate them and figure out the best rank. Now, of course, since we only have now one search engine, so this problem no longer exists. But it's great, it's an awesome search engine. But this problem is, of course, NP hard, even when you have collections of pairs. So what I want to try to understand is why is it difficult? What about this problem that is difficult? I mean, is it always difficult or is it difficult for pairs only? So here's an example involving three subsets, set A, set B, and set C. Set A has products 1, 2, 3, 4. Set B has product 2, 3, 4. Set C has product 3 and 4. And for each product in each set, we have the cost coefficient, right? So CJS. So now we want to write out what this rank aggregation problem looks like for this example of three sets. Okay. And by the way, I do want to highlight here that this set collection of subsets is what we call a nested collection. A contains B, contains C. And that occurs all the time, especially in revenue management context when an airline open or close different fare classes. So you create just nested offerings of fare classes. Okay. So then now we want to write this rank aggregation problem for this example. So what I want to make an observation here, if you look at the inner sum in this optimization, I claim that there will be exactly one term in that inner sum that's non-zero. Because for every ranking sigma, for every subset S, there will be exactly one product J in that set S that is a top rank item, and that is the J for which this indicator will be 1, and you pick up that CJS. So we can write the rank aggregation problem as this seemingly simple optimization problem, right? I just need to pick the top rank item X from A, the top rank item Y from B, and the top rank item Z from C that minimizes objective, ZXA plus ZYB plus ZZC, subject to the constraint that X, Y, and Z are consistent under some rank. Right? This seems almost like a simple optimization problem. You can just sort of literally want to separate each of them and optimize them separately. You can't do that because of this constraint, right? Because you cannot just arbitrarily pick X, Y, and Z. For example, here's one example, a triplet of X equal 2, Y equal 3, and Z equal 3. That, I claim, is never a feasible solution. It can never be. Because in order for X to be equal to 2 is the top rank item in A, so 2 must be preferred to 3. But in order for Y to be equal to 3, that means 3 is the top rank item in the set B, so 3 must be preferred to 2. So I have a situation 2 is preferred to 3 and 3 is preferred to 2. And that can never happen under any ranking, because a ranking is always a linear order, so you can't have cycles there. Okay. So again, this simple example here illustrates that top choices from different sets are not independent of each other. You can't just independently choose them. And that's why the problems in this worst case is NP-hard when you have collections of pairs. But then what can you do? So it turns out that even though top choices are not independent, conditional choices can be very independent and can be very, very useful. Okay? And so what do I mean by conditional choices? Same 3 examples. Now let's start with suppose that I set the top choice Y to be 2. And I asked this very naive question. I said, well, given my top choice Y equal 2, what are the choices of X in the set A that are pairwise consistent with X? Okay. So if Y equal 2 is the top choices here, that means 2 is preferred to 3 or 4. So the only other top choices in the set A that's pairwise consistent with Y would be either 1 or 2. Okay. And the same thing here happened that given Y equal 2, the top choice Z that is pairwise consistent with Y is 3 or 4. Okay, so again, I haven't done anything. Just ask these 2 simple questions. But the most remarkable thing now happens. For this example, pairwise consistency between X and Y, Y and Z imply global consistency across X, Y, Z. Okay, and that's not always true in general. Okay? Here's an example, and the reason for that is if you look at all the possible triplets, and there will be 4 of them. 1, 2, 3, 2, 2, 3. Wait, 1, 2, 2, 3, and then 1, 2, 4, and 2, 2, 4. Each of these 4 triplet is consistent with some rank. So for example, if I look at the triplet 2, 2, 3, that is consistent with an ordering that put product 2 as the most preferred product, okay, followed by product 1, followed by product 3, and followed by product 4. And of course, there could be many ranking that is consistent with this. Okay? So now, this is not true not for Y equal 2. The same observation also true for Y equal 3. And it's also for Y equal 4. Always. And so what we have observed in this simple example that we have shown here is really a remarkable property, which is that whenever, for every choice X in A, Y in B, and Z in C, whenever you have pairwise consistency between X and Y and Z, the triplet X, Y, Z are also globally consistent. And it's true here. And this property that we found here is what we call rational separation. Whenever we have such a property, okay, we say that the set B rationally separates A from C, and we write this as A and C being orthogonal to each other. Well, they're not orthogonal in the vector space sense, but in the decision-making sense, condition on this set B. Okay. So this is sort of what we mean by conditional independence. Again, it's not related to conditional independence of random variable because there's no randomness here. These are choice-making. And of course, we can extend these notions of rational separation to not just 3 subsets, but any 3 collection of subsets, script A, script B, and script C. Okay.
So this is the property of what?
Property of collection, of the collection of subsets. So it's the property of collection. And for this collection of nested sets, we have this rational separations. Okay. So now the next questions you want to ask is, okay, good, that's interesting observation. So what do I do with it? How does that help me solve the rank aggregation problem, which is how we could compute the limit of rationality? Now, in order to take this abstract concept of rational separation and solve the limit of rationality, we need a graphical representation of rational separation. Because they can do is I can take this collection of subset, translate it into a graph, which encapsulate this rational separation property. And then whatever we want to solve, just run it on that graph. And that graph that has a property is what we call a choice graph. Given a collection of subset script M, an undirected graph G is a choice graph of M, if and only if the following condition is true. One, the nodes of G correspond to the subset in the collection. And so that's not too far. The second one is that whenever we have collections of node, whenever a collection of node, which is the collection of subset, B separates collection A and C in the graph G. So this is a graphical separation, meaning that every path from a node in A to a node in C must go through some node in B. We must also have that B rationally separate A from C. Okay. Now, please note that choice graph is not uniquely defined. For example, given a collection of subset, I can just give you a complete graph. That's a choice graph. It's not very useful, however. Right, because a complete graph is always a choice graph because this condition is never satisfied.
Sorry, what are the edges?
The edges are created so that it satisfies problem. So let me give you an example. This is the same three collections I had earlier. Okay. We know that B separates A from C. So a choice graph for this context would be this one. It's a line graph. So this line graph satisfy the rational separation property, right? Because B separate, so this B separate this A from C in the graph, and we also have that B rationally separate A from C.
It's not if and only.
No.
That's why the complete graph satisfies.
That's correct. That is very important. Now, yes, that's correct. So now, and again, you can always show that whenever you have a nested collection of subset, a choice graph, a line graph is always a line graph is the choice graph for that collection. Okay, so that's an example of a choice graph, and I'll give you a few more as we go through the rest of the talks here. So the question is, how do you use this? What good does it do? So again, here's the rank aggregation problem that we want to solve. Okay. And then we have a line graph. I mean, a natural thing to do at this point is to set up some sort of dynamic programming. So you set up a value function at each node in the choice graph. A node here is now a set. So a value function and a set defined for every element in that set is simply sort of the natural objective. Okay. And when we do this, we define a value function at the node B. And now all we need to do is to show that there's a way to link the value function at node A with the value function at node B. Okay, so get that. So what I would do now is just to show you that this can be done easily. I'm just going to copy everything we've described and put them up here. So we have things here. Okay, so now we're just going to go through a few lines of algebra. We factor out the CXA. Then instead of minimizing a Y and Z simultaneously, we minimize them sequentially. And then we have this constraint X, Y, Z are consistent. So they put that here. But then since you're minimizing out the Z, the other constraints of X, Y are consistent. And now we just exploit rational separation, right? Because now, by rational separation, in order for X, Y, Z to be consistent, it suffices that X and Y's are consistent and Y and Z's are consistent. That's rational separation part. Pairwise consistencies imply global consistencies among triplets. Okay, we just replace that. And then we just move all this stuff back again. We have that result, and that's nothing more than the value functions at node B. Now, a little bit of work will show you that for this minimum, for every choice of X, this minimum can be computed in big O of 1. Okay, so it doesn't require you to search over all the Y's and B again. And what that means here is you can show that when you have a line choice graph, so whenever you have a nested collection of subset, the limit of rationality can be computed in linear time. It's very, very fast. Okay, so that's one thing we can say. Now, of course, if you work for line choice graph, it also must work for a tree choice graph. So in a tree choice graph, you can have a set A and a children B1, B2 up to Bm. You define the value function at each node in the tree. And here's how it relates. Okay, so the value function at the parent A would just be the cost coefficient at that node. Plus now you can treat each of the child nodes separately. So you take the minimum over each of the Y's in the child node. Okay. So and again, we would run this dynamic programming from the leaf nodes of the tree. And the leaf node, at the leaf node S, the value function would simply be the cost coefficient CXS. Okay. And you take that in terminal conditions and you roll them up using the simple dynamic program. Once you get the root node, you get what you want. Now, one problem with this formulation, as stated here, is that for each X in the parent node A here, I might have to research over all the Y's again. because for each x, the set of all the y's that are consistent with it could be different. So that could give you that's a quadratic time algorithm. So we want a linear time algorithm. Okay, so we don't, each x, I don't want to have to research this over all the y. That would be n times n, that's n squared. So I just want n. So I just want to show you that this can be done quickly. Right? Suppose that you have computed the value function all the way up to this node, b1 up to bm. Then what we can do is let's do some pre-computation. Let's pick a node, bi. And I compute two numbers, alpha bi and gamma bi. So alpha bi is the minimum of the value functions of all the elements in the set bi. And gamma bi is the same thing, but you exclude those elements that's in A, in the parent node. Now, computing this requires big O of n, little n, the number of properties, you have to search through all of one. But you're going to do it only once, and once only. You never have to do this again. Because whenever it is, you compute this minimum, for each x is the lookup operation. Right? So for every x in an element of A, if x belongs to B, doesn't belong to bi, you just report alpha bi, which you have pre-computed. And if x belongs to bi, you just report the minimum gamma bi and the v of bi. So that's a minimum two numbers.
Just a clarifying question. So
Yes.
when we had a line choice graph,
Yes.
that represents the nested set.
Collection.
A collection of the nested sets. And now here you have a tree, so that will represent, that will.
Oh, that's great. That's the next slide. I have it ready to show you what are examples of collection of subsets with the tree choice graph. That's right here. So after I state this theorem, it's going to be right there. So for tree choice graph, the aggregation problem can also be solved in linear time. Okay, so it's the total cardinality of every set in the collection. This is how many parameters you have in your optimizations to begin with. And let me give you examples of tree choice graph, collection of collection of subsets that results in tree choice graph. So one is what we call a laminar collection. Okay, what's a laminar collection? The collection of subsets laminar, if you pick any two subsets, either disjoint, okay, or if they're not disjoint, one must contain the other. So taking two subsets A and B, either A intersect B go empty, or A is contained in B, or B is contained in A. That's that. Now, the question is, when would laminar collection arises in practice? Okay. So here's one. It might arise when customers search for a product using this elimination by aspect process. So suppose I'm searching for a flight, say, from LAX to Toronto. Okay. So by looking at various different criteria. Suppose I want, say, a morning flight. Well, these itinerary 1, 2, 3, and 4, those are morning flights. So what I see on the screens are 1, 2, 3, 4. Those are flights. But then I say I want to refine them further. I want to say, well, I want morning flight with one stop. So maybe it's cheaper. So then that reuse the itinerary 3 and 4. And you can refine them further to get a single itinerary. So in that case, the collection of subset that you encounter from this process would look something like this. So you'll see the whole assortment, you narrow it down by different features, you get a smaller and smaller subset. And that choice graph is a tree. Okay. Now, another one that we see very frequently is what we call a differentiated collection. So we were looking at soup brands carried by different stores in our chain. So what often happens is there's always a core subset of brand like Healthy Choice, Progresso, or Campbell that every store seems to carry. And then each of the store would augment onto that core collection with something that is, say, location specific. In Detroit, might have Health Valley Pacific. St. Louis might add a private label, or Indianapolis might add, say, a Hormel graph, for example. Okay, so that's an example of the tree choice graph. Now, I also want to mention one really cool thing about tree choice graph is that you don't need to run this dynamic programming. I mean, that's if you don't need to code them, it's always better. You can actually solve for the rank aggregation problem using a linear program with very compact number of variables and constraints. Okay, so every problem, discrete problem, can be always represented as the binary integer optimization. Okay, so this is a rank aggregation problem. So choose CIS, XIS, where XIS is either 1 or 0. 1 if I is chosen from S, 0 otherwise. And X was subject to some constraints that is consistent under some rank. All I want to show you is that let's see what these constraints mean when you actually, what kind of inequalities is imposed. Sorry. So if you look at any two sets, A and B, and a point R in the middle, if X is chosen consistent with a ranking, if this point R is chosen from the set A, so it is the top rank item in A, it must also be chosen in the set A intersection B, because it must also be the top rank item because it's a smaller subset. So we can write this if-then statement as the following inequality. XRA is less than or equal to ZR of A intersection B. So whenever XRA is flipped to 1, the set RA must also be flipped to 1. Okay, so that's and you can do the same thing for the set B, and we have this normalization constraint that exactly one item will be chosen from each set, A intersection B, or B. And it turns out that these 5 constraints are enough. You can throw them into your optimization problem and pretend that they're real numbers. They're non-binary. And you solve them. It's a linear program. It's a very compact number of variables and constraints, and it's always integral. So you can just pick up the answers right there. And then these linear programs are very small, so it just take like minutes, so seconds. Okay, so that's that. I have 2 slides.
And also a small true width.
Oh yes, that's see. I don't know if that's good because you guys are way ahead of me. That's exactly the next question. The next slide. It's coming up exactly. The next question is what happened when you're dealing with arbitrary choice graph. Okay, so here's an example of a choice graph that is not a tree, almost like a tree. Okay, so cycles in the end. So as Renato said, what we do is perform a tree decomposition. What's a tree decomposition? So okay, you guys know more about this than I do, so I will go fast. So a tree decomposition is essentially a merging of nodes so that the resulting becomes tree. So for example, we can merge or set A, B, and C into one bag, let's say a green bag. Okay? We can put the set B and D into another bag, let's say a blue bag. And then we put D, E, F in another bag, say a red bag. And now the green, blue, red bags are now form a tree. It's connected by this. But that's a tree decomposition. There are many, many tree decomposition. Okay, so here's a formal definition. Given a choice graph G, a TG is a tree decomposition if the following happens. The nodes of the tree decomposition is a collection of bags. Okay, so we have a green bag, a blue bag, and a red bag. So that's true here. And what are these bags? So these bags must have the property that when you take the union of all of them, you must get the entire collection back. That's not necessarily true here. And for any edge in the original choice graph, okay, there must be a bag containing it. And that's also true here. And the most important property of the tree decomposition is the running intersection property, which means that if you have any 2 bags, which has a set in common, that set must always occur in every bag in the unique path connecting the 2 bags. So that's a running intersection property. Now, one of the most important measure of performance measure of a tree decomposition is the width, which is the maximum size of the bag minus 1. Okay. Now, you can then take the minimum of this width over all the possible tree decomposition, and that's the tree width of a graph. This is one of the most important and actively researched quantity in graph theory. Many of you here works on this problem. Computing this tree width, unfortunately, is NP hard. So, but what is important, however, for us that we want to know is that tree decomposition preserves rational separation. So what I mean, we can still say here that this blue bag rationally separates the green bag from the red bag. So what that really means is that you can then, instead of if you have a choice graph that is not a tree, you can do a tree decomposition. Okay, now finding the optimal tree decomposition, that's unfortunately the subject of a different talk. So, and many of you here have more experience in that. You can say that the rank aggregation problem can be solved in the in the tree decomposition, so the running time is n to the tree width. Now, of course, we would like to end here, but unfortunately, there's one thing that one of the last slides, which just happened to be important. So what if the choice graph has a large tree width? And the reason why this come up is that one of the most important collections that we really need to solve, at least the one I wanted to solve to start, is the one that occurs in retails. And that's what we call a K deletion graph. So this is what happens when at most K items are stock out. Okay. So again, so here's the setup. If every item's on the shelf are available, so that's this n. Suppose if one item is stock out, you have n minus 1, n minus 2, n minus 3, or n minus 4. Suppose you have 4 elements. And of course, if 2 items are stock out, you have n minus 1, 2, minus 1, 3, etc. Okay. The corresponding choice graph is these things where you have edges between nodes in consecutive levels. No edges between nodes in the same level, and no edges jumping for more than one level. Okay, so that makes sense. Unfortunately, this particular choice graph has the tree width of n. And you can show that by showing that there's kn plus 1 minor embedding in here. So if you start contracting edges in this node, you can make every node here all connected to each other. So that's like a complete graph of n plus 1 nodes, so the tree width is n. Okay. So that really doesn't really work. So we can't use what we discussed on the previous slide here. But the problem here, on this particular problem, it's easy. Because here's the setup. All the sets in this collection is very big. It's size n-2 or more, n-2, n-1, or n. So what this means here is that in order to find out what the top rank item in each set is, I don't need to maintain the whole ranking sigma. All I need to maintain is top 3 items of each ranking. Right? Because if I maintain top 3 items of each ranking, one of that item will be in one of these sets, because each set is the size n-2. So that means that all you really need to do is to maintain 3 items. So then maintaining top 3 items of ranking is way easier than maintaining every ranking, so that's n-cube. And again, so the next thing you have to understand, we need to do is to try to find a way to abstract that and find out to describe that in general. And you can do that. We have this notion of called choice depth. So we have a 3D composition of a graph G. We define this concept of choice depth to be the spread, the maximum spread between the size of the largest set minus the size of the smallest set, and you maximize it all the bags. And you define the choice depth of the graph in the same way. And again, the idea here is for this k deletion graph, the choice depth is k. So for this particular graph, which is tree width n, choice depth is exactly 2. Okay, and you can show that you have an algorithm that runs scales with the choice depth of the graph G. And then just a final touch is that we have 2 performance measures, tree width and choice depth, and we know that the running time is exponential in choice depth and tree width. You can also prove in our paper that the pairs collection, the one that's really hard, is NP hard, both the choice depth and the tree width is at least n. So that's why this is on. Now, but that doesn't complete the answers, but it answers all the questions we asked. And that's, I only have 14 slides. That's it. So plenty of time. Questions? Clear?
So for the motivation here, right, is that stuff gets stocked out, right?
Yeah.
But the reason it would run out of stock is because it's very popular, right? So you could have like a richer generative model, right, where it says the thing that gets stocked out is going to be the almost surely going to be the most popular one. And that would right.
Yeah. So that's correct. But it could also be a situation like there could be promotions on that. So yes, I see what you're saying, that it is popular, but it's popular because of a promotion. And we have we have a way to partially answer your question. If we know that some items have promotions, how do you account for those and incorporate the formula? It's not as clean as these, but yes.
Hi.
Yes.
A remote question.
Yes.
Can you say a little bit more about the semantics of the edges in this graph in general? Because you gave a lot of examples, but it wasn't clear to me exactly what the semantics is. If I give you an arbitrary set of collection of choice sets, for example.
Yeah. So you're hitting all sort of the questions the referees asked, and these are hard questions. So. We have, I guess, one way. I think we don't have so. I think right now these edges encapsulate the rational separation property that I defined earlier. But I think maybe one way to answer this question is right. For example, how would given an arbitrary collection of subsets, how might we go about and construct such a choice graph?
Right, because I'm thinking of the analogy with graphical models and
exactly. That's good. But now in the graphical model, constructing a most parsimonious graphical random graph, or let's say Bayes net, that's a very hard question.
Yeah. Well, except there are natural ways to build it. Sometimes you rely on causal intuitions. I can't always construct the most parsimonious one, but I can take an arbitrary ordering of my variables, and I can construct a Bayes net that way. And it isn't obvious to me how that would work here.
Right? Okay, so I think certainly, so in our paper, we have a detailed discussion of how we might go about and constructing that. Now, the only thing why I didn't talk about that here is because it's I can't really prove anything clean about them. But we certainly have heuristics, something similar to what you just described. Take an arbitrary ordering of the sets, and when like do checking between the different. So we have a heuristic for doing that. The reason why I didn't talk about here is I really don't have any clean, beautiful theorems to say, so that's why. But it's available in the paper.
Okay.
Does that answer your questions?
Yeah, thank you.
So sorry, just so that I understand correct. So you're saying if I give you an arbitrary collection of sets,
we have a heuristic
but
for constructing a choice graph.
is there a way of measuring like how accurate the choice? Like, what would be a way of saying that this graph closely approximates the
because
model?
we can check the definition. So
you can check the definition of choice.
So you can verify that it's valid.
You can verify that it's valid. That is correct.
But
You can find
if
the
it's
smallest one.
Yeah, but find the most efficient one. I don't know how to do that. For example, a complete graph
right,
is
you can
always
start with a complete
you're gonna
graph,
start removing edges.
and then if it violates, you put it
Then,
back.
but again, I didn't want to talk about that because that sounds
that sounds
kind of silly. So yeah, that's a hard. I mean, that's one of the things we are working on right now. But I mean, this is the problems also in graphical models.
Do you think it's NP-hard, this problem? It sounds NP-hard.
Probably.
It's
This is one of the polls that we have right now. We have a heuristic. We send it to the referees, but
well, the input is exponentially sized, right? Unless it's you have an implicit way to express that set.
I mean, all of these things that you kind of came up with the graph already.
I agree completely. I agree. I completely agree. Yeah. So that's one of the issues of sort of a general all-purpose algorithm for constructing choice graph or arbitrary. So what we have done, however, we have like a lot of times when we work in our data set, what you can do is we have this idea of approximating it. So for example, in our data set, it may not be exactly like a K deletion, but it's close enough, for example. And we have that, I use that approximation, and it turns out performs really well. Like, the value, we can test it out numerically. But again, it's nothing I can say theoretically, so that's why we mentioned that in the paper. It's just not on the slides at the moment.
So this was about the family of collections that make the problem tractable.
That is correct.
What about the family of rankings that make the problem tractable? Is there anything on those?
Yeah, we have not. No, we have not looked at that at all. But that's a good question. That is a good question. Yeah, we have just now looking at family of subsets. Oh yes, no, we have not looked at that at all. Thank you so much. Really, thank you.